All right, continuing on with our examples from chapter 3, we are going to be looking one more time at the empirical rule, and we're going to be using what Triola classifies as usual amount of data. And in terms of usual, what we're looking at is 95% of the data falling within 2 standard deviations of the mean based upon symmetric data, so following the empirical rule. So our example says, for a sample of blueberry cakes, the mean weight was 500 grams and the standard deviation was 12 grams. In what weight range would you usually expect to find blueberry cakes from this population? So because we don't know what the population is, we're going to use sample statistics to help us determine what we would usually expect. So because of the word usual, so if I take just the meaning of the word usual, that means that I'm looking for 2 standard deviations. So usual means 2 standard deviations. Now we don't have the standard deviation of the population, so we're going to substitute in the sample standard deviation to account for that as well, because what we're trying to do is figure out what's going on in the population. Very seldom are you going to know population information. So what I'm going to be doing is I'm going to be finding x bar plus or minus 2s. So I'm just going to do a substitution problem here. The x bar, that's the 500 milligrams, that's the average weight in a sample of cakes, and then plus 2, and then times the standard deviation. And my standard deviation is 12 grams. So now I have 500 and then plus or minus 2 times 12. 2 times 12 is 24. And so I'm going to expect to find the weights of blueberry cakes of 500 minus 24 up to 500 plus 24. And that's going to give me the weights of 476 grams to 524 grams. So how I would interpret this is I would say I would usually expect the weights of blueberry cakes from this population to weigh somewhere between 476 grams to 524 grams. Or I could say I have 95% confidence, so there's 95% probability that the weights of most average blueberry cakes will be between 476 and 524 grams. Now in terms of inferences, what we could do with this is we could say, okay, well maybe one day we go to the bakery and we take a sample of cakes that they've made, and we find out what that average is. And then we take a look at it and we see if the average falls within this range of data. And if it does, then we're pretty satisfied with that. If it doesn't, then maybe we're less than happy, and maybe we're thinking, maybe this baker is baking a little heavy, right? Making the cakes bigger than they should, or maybe they're baking a little light, making the cakes a little lighter than they should. And that wouldn't be good business practice. We'd want things that are as consistent as possible. And of course, we know with humans, we're always going to have some type of human error, so we want to watch that. Okay, now moving on. We're going to also be discussing what happens if we don't have symmetric data. Well, if we don't have symmetric data, then we would have Chebyshev's rule to apply. Now, Chebyshev's theorem, or Chebyshev's rule, it's usually called a theorem. Chebyshev's theorem says that our expectation for percentages of data within a certain number of standard deviations looks like 1 minus 1 over k squared percent of the data, where k is going to represent the number of standard deviations from the mean. And k has to be greater than 1. So this rule doesn't work quite the same way that we have the empirical rule written. The empirical rule says this percentage of data based upon this number of standard deviations, and it's good for 1, 2, and 3 standard deviations. Well, Chebyshev's will work for more than one standard deviation, so there's a difference there. And you can have any amount of standard deviations. It would work for 1¼ standard deviations, or 3 standard deviations, or 2.7 standard deviations. We can't say the same of the empirical rule. So they're just a slightly different usage, first of all, but they apply to different types of data. So the thing that we need to remember about this rule is it's mainly for skewed data. Now we can apply it to symmetric data, but remember that it's over generous. It says at least this, so it could be that there's actually more less percentage in there or more, depending upon the actual shape of the data. So what we want to take a look at here is for the percentage within 2 standard deviations of X bar for the blueberry cakes. So our K in this instance is going to be 2 because we want to know for 2 standard deviations. So Chebyshev's would say that it's 1 minus 1/2 squared percentage. So this gives us 1 minus 1/4%. And 1 minus 1/4 is 3/4. And 3/4% is, of course, 75%, because in order to get this as a percent, you have to change 3/4 to a decimal, and 3/4 is a decimal is 75. And so this is 75%. So that would be the percentage of data according to Chebyshev's that would be within 2 standard deviations of the mean. Now this varies because we're not talking about symmetric data. So we have less of the data that's expected to be within 2 standard deviations, because skewed data, we could have the mean being right here, and 2 standard deviations could be a lot narrower than what we would expect it to be on a bell-shaped curve. So if this were the bell-shaped curve and here was the mean, 2 standard deviations would more than likely lay out this far. So this range here would probably be less than this for a skewed data set. So we see this conservative estimate of percentages, and it's read as at least 75%. So we have 75% as compared to the empirical rule, which says 95%. All right, now moving along after our comparison here, let's talk about using the empirical rule essentially backwards. So instead of having the percentage of data being told by the standard deviation, or using the standard deviation and the mean to tell us a range of values where we could expect a certain percentage, this time around we're going to judge a certain set of values as having some percentage of data between them. And in order to do this, what we need to find out is how far away from the mean our values are, so we can then interpret in terms of percentages according to the empirical rule. And in order to do this, what we need is this thing called a z-score. And the z-score is just based upon the simple fact that we have X bar plus or minus some number of standard deviations from the mean. So this number that we have right here is comparable to this z-score. So that's what we're going to be taking a look at finding here. So what I want to know to find out the percentage of the data between 2 certain values is I want to know what the value z-scores are, and then I can relate those z-scores back to number of standard deviations from the mean, because that's what a z-score tells us, is the number of standard deviations from the mean. So let me just write that down really quickly. Number of standard deviations from the mean. So what we have is our z-score for 512. Well, 512 is our x value, our random variable, minus the mean. If we're talking about the blueberry cakes here, the mean was 500, and then divided by the standard deviation. And for the blueberry cakes, this is 12. So what we have is 512 minus 500, which is 12. And that's divided by 12, and this is 1. So what this means is 1 standard deviation. And because this is a positive value, that tells us that our observation, our x, is above the mean, and so this is above the mean. And so that's our z-score for our 512. Now we'll look at our z-score for our 488. So our observation, our data point, our value for our random variable, 488, minus our mean, 500, and then divided by our standard deviation, 12. So 488 minus 500, that would give us 12. And it's negative 12 because 488 minus 500 is a negative number, right? It's below the mean. And then divided by 12, which gives us a negative 1. And again, it's that negative 1 that's going to tell us that it's below the mean. So we have 1 standard deviation below the mean this time. So again, it's the negative that shows me that it's below the mean. So another nice thing about finding a z-score is that when it's done correctly, the random variable, the observation's value minus the mean divided by the standard deviation, then we're going to know based on the sign whether our value is above or below the mean. So now based upon the positive one and the negative one, we know that the values are x bars, right, our x bar 500 plus or minus 1 standard deviation, plus 1 minus 1, plus 1 minus 1, and then our standard deviation. That's what gave us these two values right here and here. And because of this being 1, right, 1 standard deviation, according to the empirical rule, we have 68% of the data within 1 standard deviation of the mean. So 1 standard deviation, 68%, is within 1 standard deviation. So we have these values, 48 to 512, that would be 68. We would expect 68% of the data to be within those values. Now in terms of looking at this as an inference that could be drawn, is we could actually go back to the data and we could say, okay, we expect these, and we could then look at the weights of cakes and we could actually count them up and say we had 20 cakes, right? And what number of those, what proportion of those were between 488 and 512? Oh, 68%, right? 68% is within there, or at least 68%. Oh, that fits the empirical rule pretty well. Looks like we're actually have some symmetric data and it's within the expected range. If it's not, if it's less than that, then we begin to have maybe some suspicions about the weights of those cakes, which would maybe warrant some further investigation. So these are the things that we're looking at with our inferences based upon the empirical rule. Now we've already talked about Chebyshev's, so I'm going to go ahead and skip on to this next example. And